So with Nigel and Mike, you've really seen kind of the state of the art right now that startups are pursuing both the data center as well as on the edge, really pushing the limits of what's possible with performance and performance per watt. One thing that Nigel touched upon was the Colossus, this first innovative computer, and that really kind of speaks to the heritage that the UK has in fundamentally developing computers and computing architecture. And one fundamental type of computing architecture, of course, is quantum computing. And quantum computing is something that if we can solve, we would really revolutionize the kind of problems that all of humanity can tackle. And it's great to see that the UK has its own representation in terms of a startup that is pursuing quantum computing. So I'm very happy to welcome Ilana Wisby, the CEO of Oxford Quantum Circuits. Ilana, please come on.
Hi. Hi, thank you. Thank you so much for that kind introduction. So we are Oxford Quantum Circuits. We build quantum computers. We specifically build quantum hardware. So we're taking a bit of a change of pace from some of the AI chip type stuff we've been talking about. But in actually listening to those things, there's actually quite a lot of parallels compared to the processes that we're currently going through. We're just a lot earlier. So just a show of hands, who knows anything about quantum computers? Oh, nice. Excellent job. So this is kind of aimed at an introduction of quantum computers with an AI kind of tilt to it, but here goes. So first of all, for those of you that aren't already interested in quantum computing, why should I care about quantum computing? Well, as previously touched on, quantum computers will revolutionize the kind of calculations and provide an entirely new form of computation that's fundamentally not possible with classical computers. So inherently, a quantum computer can, for example, simulate, at the smallest scale, quantum interactions between individual atoms of matter, which you fundamentally cannot do with classical computers. Even if you have some of the world's biggest supercomputers, there are a number of problems you cannot solve at the moment. So that's a really exciting side of it. On the other side, you've probably heard about speed up. So the potential of speed up obtained through using quantum computing is also a really exciting element. Sorry, it's very strange because the rain is quite strong. So I think as it's been already touched on, the opportunities for quantum computing are very, very diverse. So we tend to think of this in two ways. So on the left-hand side here, we've got the quantum laboratory. This is anything to do with simulation. So if you have any type of materials design process, this is where that will be really useful. And of course, that's got applications across battery technologies, across healthcare with the drug discovery process, for example, catalysis, fertilizer, trying to understand, for example, the nitrogen fixation process and how you might do that at room temperature without the incredibly high amounts of energy that currently is required within that area. That's all things that quantum computing could do. On this side of things, we tend to think about early stage applications appearing with commercial viability in the next 5 to 7 years. On the other side of things, we have the quantum boost. So with this, this is much more about any type of large-scale data processing and speed up in that sense. So in this way, you're utilizing the fact that quantum can provide parallel computation as opposed to having to do linear computation. And of course, that's got applications across many industries, particularly around recommendation and optimization engines, for example. But of course, the key point here really is that the applications are wide-reaching and yet unknown. We're still at quite an early stage point in this process. So as we begin to develop quantum computers and we can start to play with them, we'll learn more and more about the kind of applications and opportunities that quantum computers can provide. So touching on what might be more interesting for an AI type, and this is where I'm a hardware girl. I've got a PhD in experimental quantum physics, so the algorithmic side is something that's less in my comfort zone, but fortunately we have some very good partnerships and collaborations with people that do work on the quantum software side that have been able to help me understand exactly what this might mean fundamentally for quantum computing in AI. And for example, these are some of the things that we've got. So With the top one here, with data generation, with quantum computers, you can start to generate new data on the fly. This would be incredibly useful for, say, materials properties and understanding those without full sets of data. On the other side, with model representation, now this one is a little bit more contentious. It's much more kind of at an academic type level. But with a quantum computer, you could start to think about simulating systems, whether they're quantum systems or classical systems. So this one's a little bit more contentious simply because a lot of the advantages that we sell for quantum computing are based on quantum computers being able to simulate and replicate quantum systems. So why would it be better at simulating or replicating a regular classical system? So there's still areas of exploration to be done in there. The final one, of course, is quantum speed-up. So this is much more around large-scale data processing with recommendation engines that might start to provide solutions to, say, for example, the Netflix problem, especially when you have incomplete data sets. There was a paper out, I think there was like some 16-year-old that said that actually quantum speed-up doesn't exist. So there's been some debate about that, but apparently it does, so we're all good. And actually on the speed-up side, if we start to think about, so my understanding is that we can do linear regression like pretty well. But actually, if you start to think about topological solutions, so larger scale or broader scale feature recognition, that's something that quantum computing would be able to do. And there are a load of academic papers to back this up. Now I can move on to things I feel much more comfortable talking about, and then I'll turn this on its head and say, what can AI do to help develop quantum computers at the end? So a high-level overview of actually what quantum computing is. It's based on quantum phenomena, which is very, very well described by Feynman. So if you want to learn more about this, check out the Feynman lecture series. They're online. They are absolutely incredible. He communicates concepts in a very accessible way, but then backs it up with a buttload of maths. So I really like that approach. But we're going to summarize it in 2 slides. So quantum phenomena, we need to think about the fact that energy is now quantized. So energy is now discrete as opposed to a continua. We need to also exploit the concept of superposition. So this is where a quantum state can be simultaneously in more than one state at the same time. And we'll touch on that a bit more in a second. And then the final one is entanglement. So this is the fact that if you have one quantum entity here, one quantum entity here, you can join them up and they will behave in tandem with each other or dependent on each other, even though they're not physically interacting. We all got that? Great. So we start to think about the quantum bit. This is the building block for the quantum computer. The quantum bit is typically described through this thing here, which is called a block sphere. So I like to think about this as the world. So if we have the North Pole, if we have the South Pole, we know that humans can exist all the way around the world and can operate in parallel. We're all here. Some people are in Tokyo, some people are in Australia. And that's very much the same with a quantum bit. So I can define a state, and it can be either a 0 state or a 1 state, or it can also be anywhere else on the edge of the world. And then in that way, you have a vector, and you can have many of those vectors in superposition all around the edge of that block sphere and calculate them all at the same time. So you therefore don't have to have one bit with one piece of information. You can have one bit with many, many pieces of information operating on that same sphere. And yeah, this is basically the fundamentals of quantum computing, so you're doing well. There are some maths. We start to think about describing them with Hamiltonians, which you're probably actually way more familiar with than typical audiences. But yeah, so there are maths behind this. That bottom one there, you have a wave function that's describing, so the 0 state is having a vector which is up, the 1 state is having a vector which is ironically down, and then if you have a wave function of a mixture of those states with a given amplitude, that's the point where you're operating around the edge. So how do we think about building a qubit, a quantum bit to start operating on? Well, there's actually many different ways in which you can think about building a qubit. Fundamentally, what you need is that discrete energy level splitting, so you can have 2 energy level states that you can start to operate between them and start to manipulate them. And nature actually gives us a number of natural qubits. So if we think about silicon quantum dots, natural atoms, impurity spins, trapped ions, they're all systems which give us a qubit state that we can start to manipulate and start to do computation with. Oxford Quantum Circuits, we work with superconducting circuits, which I am biased, but is definitely the best approach to quantum computing. Superconducting circuits are man-made systems, so they're engineerable. They're very much similar to standard microwave circuit type things, but of course they use superconducting metals, as the name might suggest. And this is actually an artificial atom. So these ones are natural atoms, whereas superconducting circuits gives all the maths, all the same quantumness behind it, but in a man-made, controllable and engineerable way. Superconducting we lost the kids. Okay, so if you want to think about building one, you start with a basic LC circuit. So you have an inductor resonance circuit. Someone's laughing. It really is this simple. It's a really simple circuit. It's got an inductor, it's got a capacitor, and of course they're made from superconducting metals. Now, superconducting metals, in order to superconduct, need to be below their transition temperature, which tends to be around, well, transition temperature tends to be around 0 to 10 Kelvin. Depends which metal you're working with. Typically, we work with aluminium or niobium nitride. So you need to get them cool. Now, getting them cool is actually pretty simple. So we have these fridges, and they work very, very much like the fridges at home, except they pump on cryogenic gases as opposed to air. And in this way, this means we can get down to millikelvin temperatures very, very simply. And there are numerous suppliers that provide these things off the shelf. So we don't think of that as a problem. What we then need to do is take it from that 9, 10 Kelvin, which is minus 263 degrees, down to 30 millikelvin or 10 millikelvin. And at this point, we start to open up that degeneracy state. So we start to open up that quantization. So then we have two discrete energy levels that we can start to manipulate around, because quantum requires very low temperatures or very low energy environments. So it's not obviously just an LC circuit. There has to be something more than that. And actually, what makes it quantum is this magic component, which we call a Josephson junction. Now, a Josephson junction is basically a superconducting layer with an oxide layer and another superconducting layer between it. And what happens when you have a superconductor is you have electrons that then buddy up into what we call Cooper pairs, and they then begin to tunnel through this oxide layer in a specific way, which gives a non-linearity, which then makes this LT circuit not just a standard resonance circuit, but then makes it into an artificial atom or a quantum bit. So then all the maths becomes beautiful. And as I said, if you read Feynman, you'll read the maths, and it's beautiful. So this is some pictures of what they actually look like. So we have one here from Google. We have one here from IBM. We have one here from Rigetti in slightly poor resolution, so sorry about that. We also have one from OQC, and we'll talk about that a bit more. And this is the fridge. This is where it operates. So we operate the circuits down here at around 10 millikelvin. As you can see, they don't look too scary. The background here is typically a superconductor. That's usually, as I said, aluminium or niobium nitride. This is all done on substrates, typically silicon, sometimes sapphire, which again isn't too bad. And all the processing in developing these kind of circuits is very, very similar to standard microfabrication, the difference being that Josephson junction layer, which requires a double angle evaporation step. So if there's anybody here with a clean room that wants to start thinking about the future, you should think about adding in a double angle evaporator, and then we'll all be dandy, and we can all build thousands and thousands of qubits, and I want to work with you. So of course, that's about the quantum, the qubit, the device itself. But you can't just have a quantum device and then it will be dandy. What we need to think about is creating a whole computer to support that. So this is kind of my diagram of what that begins to look like and where OQC operates. So of course, you have your end user, you have a problem at your end user level. Then of course, that problem must be converted into an algorithm, which is, oh, hi Matt, something to solve. And then of course, once you've got to that point, you then need to compile it into something, into signals that your quantum computer can understand. So at that point, it goes through your quantum processor. There's some control software, some control hardware onto your quantum device. Your qubit is manipulated, it's shimmied around, an algorithm is done, it comes back up again, and we read it out, and we understand a calculation has been performed, and we can look at the signals that have come out versus signals that have come in, and we can understand that. So at Oxford Quantum Circuits, we have a very unique quantum device. It's a unique qubit architecture. So that's kind of the founding premise of the entire company. We're also working on some of the control software and control hardware layer, because if we want to develop quantum computers, we need that. And ultimately, our quantum computer will be accessible through a cloud system at this kind of layer here. We have to do some part of the compiler so people can access it. Meanwhile, we have quantum software people working on this side of things and end users, and it's as simple as that. So why don't we have a quantum computer today that's useful? So to clarify, there are plenty of quantum computers in the world. We just can't do anything commercially useful with them yet. In order to get to a point where we can do something useful on them, we need to have systems that are bigger. So typically 50 to 250 qubits, we can start to do commercially interesting problems. We need to have systems that are a higher quality. There's a load of terminology that you can get bamboozled by about fidelities and error rates, but ultimately, they just need to be better. You also need to be able to control and manipulate every individual qubit very well as turn on and off the interactions between them coherently. And that's something, again, which is quite challenging. So achieving all of these three things in parallel is basically where the industry is at. We're all trying to work on developing bigger systems whilst maintaining that high quality and also facilitating that control. So at Oxford Quantum Circuits, we have a unique approach to this. You saw some of the other circuit designs, skip, here. And what you can see is you have your qubit, and then you have your measurement and your control elements that you can pass signals on and off them and manipulate your qubit. And you can see that they've started to scale them. So you have more and more qubits to your device. If you scale in this way, currently the quality of the devices goes down, which is a problem. And it's a problem that everybody like IBM, Rigetti, Google, and others are all trying to solve. And they're doing this by taking inspiration from what exists currently within the semiconductor industry, so through silicon vias or through flip shipping, for example. But quantum systems are fundamentally different to regular classical systems. So if you do that, you have some problems with some interfacial layers and two-level systems and quantum noise. So it's just not translatable. So these are big challenges which people are currently trying to overcome. And what happened was our founder, Peter Leak, who's based at the University of Oxford, saw that people were scaling very rapidly and were finding that that quality was decreasing. There we go, hard one. And he thought, well, what would I do? Because actually what they've done is taken something that existed within academia and scaled it up very quickly to meet some arbitrary milestones that really don't mean very much. What would we do if we were doing this for commercial applications from first principles? So he developed a novel qubit architecture within the university, which is called the CogX, which, if you're a physicist, has some extra meaning. And the CogX, as you can see, looks pretty different to those other circuits. So instead of having all of that control and measurement in that same plane, instead we've taken it out of plane, so we have this really neat unit cell that's very scalable. So you can just begin to copy and copy and copy and copy it in across. You could even think about having 3D arrays if you really wanted to. And we've basically decoupled everything. So you have your qubit on one layer, you have your connectivity layer on another. It's completely decoupled, it's completely scalable, it's completely flexible, because as you add more in this way, you're not adding quantum noise or mess near it. So that's what our foundations are, and that's what we're currently doing at Oxford Quantum Circuits. So we are currently building, I have no idea how much time I've got left, quantum computers. Oh, I'm out, whoops. We're currently building quantum computers to a bigger scale, right? So this is exactly what we're doing at OQC. Final thoughts were, again, bringing it back around to AI. What can AI do to help build the next generation of quantum computers? Well, we can think about automated searches for pulse sequences, for example, circuit device designs. You can use AI there for sure. People already do, as well as through smart compilation of error mitigation. And with that, I will call it a day. Just to note that we are hiring and we are also fundraising right now. So have a chat after if you want. Thank you.
Is it working? Okay. Thank you, Ilana. It was a quantum computing talk where you kept the crowd, which is really something new for me. This is a really, really very hairy stuff. We're going to have I'm going to ask Nigel and Mike to come back on. We're going to have a panel discussion to kind of dig into some of their products, and afterwards we'll do a bit of Q&A so that you can get your questions answered as well. Quite a storm. Okay, it's great hearing all of your individual presentations. I think maybe just to start off, recently Hennessy has been saying that we're in a golden age of computer architecture, and that's and we're seeing that with a reflection of the amount of startups that's happening now in building new AI companies. Do you agree with that? And what does it feel like building a new chip company today versus maybe a decade ago or during the prime days of the Silicon Valley?
Well, you're best to answer that. You were around then.
Well, thank you very much. Yeah, I was a very early employee at a company called Altera, back in the days when FPGAs were being created, and that was an amazing experience. The company grew very rapidly. It was a new technology that kind of transformed the way that people did logic design, and there's definitely strong parallels with what's going on now. But I think that this is actually more fundamental. It's like the 1970s when microprocessors were first coming out, which I don't remember. But it's just this period of new compute which needs new architectures, and so there's lots of innovation around that, and I think that there's obviously going to be some big companies that are created as a result, hopefully from here in the UK.
Yeah, I'll just quickly add that when we first started the company, it was 2012, and we wanted to be venture backed. And we were watching the amount of venture funding going to semiconductor companies year after year just approach zero. It was very disheartening. I could never believe in a million years it would have just all of a sudden skyrocketed up. But it just goes to show that it is a new wave of technology. But it took many, many years of persevering through the dark days of semi-funding, for sure.
Mike, in 2012, AlexNet was just getting invented. Was the original idea of Mythic actually to go after neural nets, or did you start off somewhere else and then you actually found fit with AI?
Yeah, so actually, I think the reason we exist right now is that we started off with a simpler problem. So we were actually the very first days of the company building GPS receivers for the Air Force. And there's a correlation step in GPS that is similar math to the matrix math in AI, but much lower precision. So we got it working at a lower precision, and then but then AlexNet came out, and we just pivoted the whole company to that. I mean, we looked at it and we said that there's no way this is not going to be huge. And then we said, okay, so now all we have to do is get the precision from 3 bits up to 8 bits. The problem with analog is that for every bit you go up, it's like 2 times as hard. So it actually took us 4 years to get that working. But it was focusing on an easier problem first that actually got us to the solution we have for analog computing. Yeah.
Thank you. Ilana, with maybe you can tell us a little about the founding story of Oxford Quantum Circuits, sorry. Both sound very techy. As you mentioned in your slides, there are a number of companies worldwide that's pursuing quantum computing. How did Oxford come about, and what are you all doing differently than maybe your global competitors?
Yeah, sure thing. So as you said, there's a number of companies that are working in this space. There's also a number of companies working, so we specifically do superconducting quantum circuits, but I touched on other approaches. So there are other companies going for other approaches to quantum computing. What happened basically was you reached a trigger point within academia that it's no longer suitable for an academic space. And with that, it probably happened about 5 or 6 years ago. And actually, D-Wave were the first kind of quantum computing company that really kicked off investment in that space. And since then, there's been more and more. So IBM had a research element that then commercialized its own technology in the last few years. So effectively, what we've seen is a lot more attention come across to quantum computing within the superconducting space, but nobody has met the kind of quantum supremacy, which is everybody hates. It's a terrible, terrible milestone presented by Google, unfortunately. Huh? Yeah. And those milestones were never met, so people started to get disheartened by it. And what happened was our academic founder from the University of Oxford, Peter Leak, saw this and really wanted to revolutionize what was going on and think about it in a different way, more commercially. So that's really where we came from.
With Moore's law slowing down, we're seeing a lot of companies pursue different means of accelerating compute as we get smaller and smaller. Does this help startups or by kind of closing the gap since Intel can't always be ahead, or does it hinder you? How does this dynamic play out for you guys?
Yeah, so I think it helps us because, again, we're in the inference space, and we're especially going after edge inference, right? And you're in it. That's an area where there's a lot of fragmentation, a lot of different opportunities, but also a lot of cost sensitivity. And there's a lot of companies that just can't afford to, go to state-of-the-art semiconductor nodes. And so, the idea that they're going to license some IP from somebody for their SoC and build a 7-nanometer SoC, we just don't see that happening. And so you're seeing, I think it's going to help us in two ways. I mean, the first way is that we're going to have competitors also try to build accelerators for edge inference. And they're going to find the only way they could come even remotely competitive with, is to be in the state-of-the-art nodes. They'll have to be in 7 or 10 nanometer, but that's just going to create a product that's way too expensive. And you actually see it where a lot of the other edge inference accelerator companies that are claiming these big numbers, they all seem to be going after automotive because right now everyone thinks automotive is not very price sensitive. I think the second way it's going to help us is really foment this chiplet revolution where people are going to mix and match silicon as opposed to building this big monolithic SoC. And considering we're going to be selling a variety of different sizes of silicon, having a chiplet strategy can be great for us. It'll give us a lot more doors to go in order to win sockets. So.
I think it does help the startups. So what happens is that if you look back, you would have semiconductors would just improve every 2 years or so, driven by Moore's law, and architectural innovation would be harder to bring to bear, and it would be the big companies that would drive forward, leveraging Moore's law to just continue to push their architecture forward and forward, probably Intel being the classic example. So as Moore's law slows down, that obviously means we need to rely a lot more on architectural innovation. And I think something which is far more fundamental is actually what we call Dennard scaling, which is the fact that we've actually reached the power density limits of silicon. And so, we've actually hit those limits at 90 nanometers, which is like 2006, 2007. So your laptop now has tens of processor cores, but still runs at 2 gigahertz, just like it did 10 years ago. But how do you get from 10 processor cores to 100 processor cores? How do you get from 10 to 1,000 processor cores? That needs a fundamental rethink in computer architecture. And it comes at exactly the same time as we start to make breakthroughs in machine learning, where suddenly we need these parallel computers, and it's fundamentally a parallel problem. So it really is about creating these new architectures that fit in a new world. I believe that we've still got quite a bit more to go with Moore's law. It's just going a bit slower, but what we're really dealing with is a post-Dennard world, and that's really what we've got to try and design around.
From
From the quantum side, I guess silicon is, when we talk silicon, we talk about Moore's law. When we talk quantum computing, I think I've heard of a different law where you also get this kind of improving performance every X months, either Rosie's law or something to that effect. I think it's like tracking the number of qubits. How do you track progress in quantum computing?
Not with a number of qubits. Yeah, so actually quantum benchmarking and understanding progress within this sector is something that is a really, really good question, right? We need better benchmarking. You can't say you have 5 qubits, 10 qubits, 100 qubits, 1,000 qubits, and therefore each time your quantum computer gets better. You know, behind that scale, quality, and control, there are a number of interdependent, very technical parameters which you need to optimize across each of them, right? So actually finding a way to benchmark and measure progress is something that we're currently all still looking at. Now, IBM have put forward a quantum volume, which is a really neat way of benchmarking. It's an algorithm that's open source that you could think about running on everybody's quantum computer. Of course, it's still manipulatable to optimize for a specific computer. But yeah, that's a really great question, and there should be a better answer.
Mike, you had a great quote from a competitor of yours, from Cerebras, about the changing nature of workloads in AI. When you all started your companies, I'm sure you had a suite of benchmarks, a set of, like, these are the benchmarks we want to win, and if we do, then we'll have a chance of competing against NVIDIA and others. How has the nature of workloads changed since the initial design of your chips? Graphcore is on the 2nd generation now. You guys are about to sample. Have those changed in a way that's really surprised you, and are the assumptions that went into building the initial products still good for what's happening out in the world of AI?
Yeah, actually, I mean, it's interesting you asked that, because in the earliest days of Mythic, we were saying 100x or 1000x better, and that's because AlexNet was so driven by fully connected, giant, dense, fully connected layers, and those fully connected layers work extremely well in our hardware, whereas, you know, convolution, the digital approaches can get leverage some advantages out of convolution, and so you naturally saw everything move to convolution because it ran so well on digital hardware, and you know, these later networks that are coming out try to get more and more, you know, weight reuse and data reuse and things like that, and so you know, the workloads did change from the early days. But I think it's I still say that's okay. I mean, because again, our philosophy is just give a vector matrix engine that's incredibly fast and powerful, and you can run convolution, you can run fully connected, you can run RNNs and things on that, and keep up. Where you don't want to do is you don't want to make really domain-specific accelerators where you literally built like a ResNet 50 accelerator chip. But in reality, that's what other companies are doing. And when you see these really big claims for numbers like ResNet 50, you look under the hood, yeah, it's full of like Winograd 3x3 accelerators and things like that. And they're going to fall into a big trap with that, because the latest network that came out of Google is going to completely falter on that time of accelerator.
Yeah. The second, with the chart you showed, the second fastest next to yours was the Habana chip. Have you guys looked into that? How are they? They seem to be quite a bit faster than NVIDIA, which is impressive, but how are you feeling versus the competition like that?
So that was energy efficiency I was showing. That was not performance. And so, you know, the two numbers that we really benchmark is performance per dollar and performance per watt. That is, and that's in my mind really what matters for inference, right? So performance per watt, you're seeing like for edge, you're seeing the really focused like 3x3 convolution accelerators start to, you know, get close to us. I'd say within 5 to 10x of us for performance per watt. But then they're really hitting this kind of ceiling where you're just not going to get much more out of digital, and you're in a state-of-the-art process. But then when you go to performance per dollar, that's where, you know, we'll have likely 10 to 20x advantages there that are just going to be really hard to recover, because we're in a cheap process, you know, getting a lot of performance out of it.
Well, kind of the point of my speech is the machine learning is a very different workload. What most of the startups are doing is they're building a better GPU, or trying to build a better GPU, incremental in some way, maybe bringing more of the data on chip, or trying to be a little bit more efficient in terms of the arithmetic. But that's not really a sustainable advantage. And there's many who are going even further and building accelerators which are very specific to one workload. ResNet, as an example, that's been spoken before. We fundamentally believe that these knowledge models will become much more complex, and that's really what we built the Graphcore architecture to support. It can do anything a GPU does, because you can connect the cores together and they can replicate whatever a GPU does, and it will do it as well, in many cases better than a GPU. But what it allows you to do is to create the next breakthroughs, and that's really, we think, very fundamentally important. The other thing I think we're seeing is that the size of the models is increasing. We're in a phase at the moment where people are exploring the size of models. And that's something that's really been driven by TPU, where you've got lots of TPUs being able to connect together. So we're in an exploration phase around how big should models be. We fundamentally believe they don't get too large because they just become very, very difficult to train. But actually what you end up with is ensembles of models, many different types of models all working together. It's kind of what happens in your brain. Not that we really know exactly how the brain works, I certainly don't, but it's these ensembles of models working together, but it's lots of processors connected together to be able to either train or deploy. And I think that is the other big difference, is people talk about inference as though the model's been trained and then it doesn't change. I think that's completely false. What happens is that the models will need to learn from experience. If a human kept on doing something and they kept on doing it wrong and you kept telling them you're doing it wrong, you wouldn't think they were very clever if they didn't change, if they didn't learn from that experience. And the same will be true with AI. We'll really need to learn from experience, even in the deployed phase. So continuous learning and being able to improve. It's a big issue in automotive at the moment, where many of these models are being created for the internet. It doesn't matter if you get the cat wrong. The accuracy of the model is not that important. Whereas in a car, you want to be safe and you want to know why it got the answer wrong, and what have you done to improve that model so it won't make the same mistake again. So things like statistical environments around the models that use Bayesian approaches. One of the things we built into our IPU is the ability to create lots of random numbers, entropy, which becomes very important in these kind of statistical systems.
We'll do one last question. We'll turn it to the crowd for Q&A. The way people treat kind of the relationship between technology and government, I feel like, has taken a sharp turn. It used to be that if you're a technology company and you supplied it to the government, that was an okay thing. Raytheon is considered to be an okay company. But now a lot of technology companies are very adverse to being providers for government and defense. I think I heard one AI startup company say, we're very happy to sell our products, but if the government asks us, I think we'll say no. And this seems like a very dramatic change in sentiment, and especially when, arguably, if your enemies have AI technology and you don't, that's not exactly serving the interest of your country. So how do you feel about this? Would you be comfortable having the government and having the Defense Department being a customer? And how would you rationalize and maybe communicate that with your employees?
So we have investment from Lockheed Martin. We have investment from InQtel, which is a U.S. group that bridges you between startups and government entities. I think that us as our leadership team and me and my co-founder, when we saw what happened at Google and their response, and then we saw what happened at Microsoft, and we saw Satya's response where he defended working with the government, we felt really strongly with Satya's views. And I'm not going to try to quote him. I can't remember what he said. It was very eloquent, and if I tried to spin something out, it'd be probably a lot worse. So I'd say just go read what he said, and then that's what we think. So
I think it's a difficult line, and we as a hardware company are slightly struggling with this, because at the end of the day, if we provide our hardware, say, to a large hypercloud, and then they go on and use that to serve government, how can we really control that? We might have some control, might be able to exercise some control. Actually, the biggest control, I think, is by being at the leading edge and being one of the major suppliers. That's how you probably get a voice. But I think it's also difficult because you think about surveillance. You know, on one level, surveillance is good, keeps us safe. But where does it become spooky? You know, and it's really about where do you draw those lines in terms of the use. So I think it's super important that as a community that we really get involved in the whole ethics debate, that we challenge people on how this gets used, we challenge people on data and how it gets used. You know, and it's really weird, isn't it, that you know, you're happy to give your data to Google, you're happy to give your data to Facebook because they give you a service in return, but you're really scared if the government uses your data. Whereas actually some of the health data that here in the UK the National Health Service holds, you know, is phenomenally important, and it's all anonymized and you know, very safe and could be used really for incredible good. So there are all kinds of lines around which government, what's it going to be used for. It's a very difficult argument, I think.
Yeah, of course, this is equally applicable to the future of quantum computing, and the UK government has taken a very cutting-edge approach to providing a quantum computing program. So the UK had the first quantum computing program, which phase 1 has just finished, phase 2 is just kicking off. I believe there are some announcements today or this week around that further. So they've been really supportive of taking the quantum industry out from academia and into commercialization of it. There are, of course, many kind of questions around what that looks like going forwards. Whether we would supply to the government or not is a question that once we've got a useful quantum computer, we'll definitely have to start thinking about. But yeah, they're interested. They would want to buy one of our computers. The other side of it is government funding, for example, and finding investment within this area. You know, quantum computing is a sensitive area. Therefore, there are certain sources of funding that we can and cannot take. Certain sources of funding that people may or may not feel comfortable with, and that's something that's really, really relevant to our area right now.
Okay, we'd love to take some questions from the crowd. I think we have some microphone ready to go, so please raise your hand.
Mr. Nigel, you started your presentation with that the thinking of decision or the human mind is working totally different than what the current technology is working with. So what do you think about artificial neural network? Is this the good approach, or we need to change this approach for something different, inspired by the human mind?
So if you look inside most of the machine learning systems, you know, what you're finding, the fundamental underlying structure is a mathematical graph, which is really defining how the data is connected together, where the vertexes, the neurons, if you like, connected by edges, the synapses, if you like. The neurons, the vertexes are really tensors, and you're doing mathematical operations on those tensors. You know, so whether it's a convolution or some other kind of transform function, for example, on those graphs. So I think, you know, that is really the way we need to think about how we build these systems. The brain is just one implementation of how you build a graph computer. We're obviously building a graph computer in silicon, and we're going to build it very, very differently. And so, you know, there's things you can learn from perhaps how the brain works, but also, you know, you're inspired by the different things that the brain does. Different parts of the brains work in different way, the plasticity in the brain, the fact that, you know, for example, you know, my example about Theresa May earlier, you know, what tends to happen is you hear these very famous people, you almost grow a neuron for that person, and it sparks, you know, lots of other connections in the brain. And so, you know, from a silicon point of view, you know, we need these highly parallel systems that can learn and can adapt, but they're going to be different from what we're building, you know, in wetware in a human.
Hi. Are there any unique fabrication challenges any of you have faced, and how have you overcome them?
No, I didn't hear the
Sorry, what challenges?
Fabrication.
Fabrication challenges.
Oh, application challenge.
Application or fabrication?
Fabrication.
Fabrication.
I was like, tons of, yeah. No, that's a great question. I think we did an initial step in 2012 or 2013 of selecting what was going to be the non-volatile memory technology that powers our architecture, that lets us cram 8 bits onto it with enough retention to at least get a day or two before we have to refresh it. And there are a number of technologies that fit the bill, and when you stack them all up, you see like phase change in RRAM and flash memory, and flash memory jumped out at us as very production stable and a mature technology. The problem we actually ran into is more of a business problem than a technology problem, because flash memory was very much a commodity, highly protected, trade secret driven piece of technology. And when we went to the initial foundries and said, we want internal access into your flash memory IP, they all told us to go away, right? And actually, back then, that's actually why a lot of academics went to RRAM and like logic flash and these other approaches, was they just couldn't get access to flash memory because it's all very proprietary. We finally got through with Fujitsu, and they gave us access, and we're off to the races. But that took years and years to get that through. So yeah, there's a lot of challenges when you're doing something new. But it's probably, I'd love to hear the quantum side of it. But yeah.
I think it's quantum has the big challenges. We're building in standard silicon technology. Billions has been invested in how to build silicon at scale, and we just leverage that. We work with TSMC as our fabrication partner and leverage their technology. But I think quantum's the difficult one.
There are still many similarities, so I don't want to stand here and be like, oh yeah, it's so left field that we couldn't possibly do it. We do take a lot of inspiration from the semiconductor industry, specifically that Josephson junction component with the aluminium, the oxide layer. That's a process which at Oxford University we've got some of the best reproducibility of. It's like less than 3%, which is some of the best in the world. But actually being able to reproduce the thickness of that insulator layer and have it very well bonded to your superconductor layer themselves is a challenge, which I would say you've still got to, if you're going to create tens of thousands of qubits, that's an area which needs to be improved. We do kind of combat that by also making sure we develop in a modular way so that you can kind of have that redundancy built in. I guess if we work on silicon, so that's useful. But obviously, when you then first go through creating qubits with different materials, you have to go through the same development of recipes, a lot of statistical analysis. So when we're starting to think about how to build higher quality qubits, one of the first things we've done actually is hire, and we're still hiring on people from industry that are used to developing new recipes from the semiconductor industry, right? So that they can apply the same 30, 40-year processes and development to these systems so we can continue to improve them robustly in that way.
Question to Mythic company. Do you have working analog silicon? Was it first one?
Yeah, we do. So basically, if you think of our architecture as a big tiled system, and I showed up there 108 tiles connected with a network on chip, and then we also had we have like a RISC processor in each tile. We have a vector engine in the digital domain. All of that has been what has been under development for the last year to year and a half. The analog portion we've been working on for 7 years, and the latest silicon we have is I think our 6th version of it, and that's the one where it has all the analog, it has the digital analog. The FPGA basically serves as the digital architecture that attaches to the chip, but with that chip we're able to feed in. I think it only has 4 million weights of capacity, so we were able to do an MNIST neural network on that chip, and the digital version of that got 98% accuracy, and our analog chip got 97.9% accuracy. So we're able to, like move the temperature around and show that it can track temperature and not lose accuracy and things like that. So the proof that we have, all you have to do is say, okay, now can they build a digital architecture around that? And if you look at our team, yes, we can. So that's what's left. And we're, like I said, literally days away from production tape out, though, as Nigel might have said, we were on a panel a few weeks ago, and I said the same thing, days away. So I need to be very careful here. But according to my engineers, we're days away. So we'll be sampling later this year the full product.
Hi, I heard Mike mention the use of RISC-V in your designs. I wondered what the panel thought the role of open source hardware would be in AI.
Yeah, I've seen a lot of RISC-V. Would love to get your thoughts.
I'll take that one first.
You know, I guess most of the open source processor projects have been focused on a fairly specific opportunity, which is how can we go after ARM and just make something which is free, particularly in the IoT market. You know, so the processors they've come up with, you know, they're reasonably flexible. Habana, for example, has taken a 10 silica core and has kind of played with that to get something out quickly. But I don't think it really hits the nail in terms of actually architecting something which is really designed for this space. It's not just any old processor will do. It's, you know, for example, we are taking a piece of data from here in the memory, a piece of data from there in the memory, bringing it to the compute, writing it back somewhere else, and, you know, we're orchestrating that all within one cycle in the processor. Different transcendental functions that you need to actually support the different machine learning functions, random number generation inside the processors. It's a very different processor design, but at the end of the day, it works with standard LLVM compilers. It runs a complete C, a ++ program, and has many similarities to other processors. But I don't think you just take an off-the-shelf processor and build anything that's going to be long-term competitive as a machine learning processor.
Yeah, for us, I think it's a similar to what Nigel said, that a bulk of the work was outside the processor. And so we have a RISC-V processor in each tile. That thing's only running at about 250 megahertz, and it's doing a lot of bookkeeping. And it did shortcut the development for us, and it saved a lot of money going with ARM. You know, so we were able to have a compiler up pretty quickly. But again, that compiler and the stuff running on the RISC-V is not doing a whole lot of really complex stuff. So we had to put a lot of thought into our vector engine, into our matrix engine. So it did actually save us money, and it saved us time. So, you know, we're happy with it.
Hi, got a question for Ilana. It's kind of themed with the temperature of the tent. How do you intend to scale the cooling? I mean, your technology depends on getting down to superconducting cooling temperatures. How do you do that in a data center, or even worse, a handset?
Yeah, that's a great question. Actually, the companies that are currently building these cryostats have much larger systems, and they're very, very ahead on the development. It's not necessarily the cooling in terms of scaling that I would be so concerned about, because you have these fridges, you can keep them cold for years, right? So you could think of a multi-fridge type system, which is kept very stable, very cold, without there being too much problem. It's actually more around getting the signals down in an efficient way within that space without compromising the cooling power. So if you start to think about the need for multiplexing of signal processing down wires, so you don't have a single wire per qubit, like that's not scalable. That's an area I would say is much more of a concern to me than how are we going to build big stable fridges.
Hi, I have a question also to Ilana, also about temperature. Is it possible to build a quantum computer which would operate at room temperature?
Yeah, absolutely. So if you use other types of technologies, for example, ions, they operate on big laser tables at room temperature. Yeah, they exist. If you do silicon, you still need cold temperatures, because ultimately with quantum you need that very low energy state. So it's finding a way to achieve that state. You either need low temperatures or you need, incredibly low energy.
Thank you very much for an interesting panel. Can I ask, what are your aspirations for your business? Should I think of you guys as trying to be like the next Intel, or do you want to be a kind of big but notable niche in a specific bit of the market?
I think this is the future of computing, and there will be big companies that will look similar to an Intel, but in this space. So to the extent you think this is a niche, actually I don't think it is. I think this becomes bigger than computing today. Then big companies will be created. That's certainly our ambition. I think there are a lot of startups out there who are fairly cynically trying to build something quickly to get bought and flip and make some money. But that's not our goal. Our goal, we've raised over $300 million in venture. Last round was a 1.7 billion valuation. We've got other people wanting to invest in the company. We're in this for the long term to build a big company and make it very successful.
Yeah, I mean, I basically reiterate everything Nigel said. I think it's very rare that these big technological waves come through, and every one of these waves, a few big companies get created out of it. And the fact that, we, all the way back in 2012 when the first AlexNet paper came out, and we said, we think this is going to be huge, and we pivoted everything through there. All the technology we developed, we pivoted it to AI. We had to go through 4 years of going in front of investors and them saying, who the heck are you? What the heck's a neural network? Analog, are you crazy? What's your previous company experience? Oh, you have none? Like, we went through 4 or 5 years of that. So we kind of, we've been through the long slog, and we really want to see something big and great get created out of this because we put so much effort into getting this technology to work. So.
Yeah, that's also our ambition, right? You don't want to build a quantum computer to do one specific problem and solve that. We're building a universal quantum computer to solve any type of problems, and yeah, absolutely. It's so cold.
It's very cold. Awesome. Thank you so much to our panelists for joining. This concludes our session. Please give them a round of applause.